Here we are once again, AI Hackerspace, 3rd of June. We're here having a cozy session in our spaceships, the log cabins, and messy offices, and some slightly more tidy looking offices with houseplants. Blair's going to be talking to us today about a couple of topics. I'm excited for this one. I've been looking forward to it for a while. So let's get right into it. Blair?
Hey there. Okay. So, is that Sean? Is the mic on? Yes, mic's on. Neat. Okay then. Fun and games. So, if anyone went to the first talk that I gave last year on unscrambling the egg, what it was a way of being able to take software. Tech software that was on one platform and use AI for moving it to another. At least that's what the talk was about, this highlight thing. But mostly what it was a talk about provability of AI. So instead of having the port actually be because the software that was ported could be tested against the original data sets, if it was generated entirely from a set of documentation and it passed all the tests, for last 20 years of data, then you were pretty damn sure that the documentation was correct. So it gave us a way of producing provable documentation for software, right? And that was very cool, because having architectural documentation that is actually correct is a luxury that few people get, and having a computer write it for you is a luxury that I very much agree because I am awful at documentation, which will be important later on, as I haven't generated slides for this because I am awful at documentation.
Like a true developer.
So we're going to be looking at this. So some background. I work for a government department, which may rhyme with Stats New Zealand.
Rats New Zealand.
Yeah. Obviously, right. So and they have a problem. They have many problems, let's be honest. But they've got a couple of particular ones, and one of which is that a shocking amount of the stats that we generate in New Zealand is done on spreadsheets, and that makes people very unhappy, and that they're not controlled properly, and sometimes the spreadsheets aren't the same from month to month, and I shouldn't be saying that stuff out loud, but it's
I might edit that part out.
Yeah. But anyway, but they're actually generally the stuff that Stats New Zealand does is in fact extremely good, even regardless of this. And so they've got these two worlds, right? Well, one is this old spreadsheet-driven SAS code kind of thing, and it's a bit dicey, right? And then they've got this newer world, which is the stuff that hasn't been implemented yet. Oh, sorry, I'm kidding. The stuff that's been implemented on newer platforms, has been written in the last 20 years, that kind of stuff. SAS stuff is a particular problem because our SAS engineers aged out. And it is very expensive to get new ones, and Stats doesn't have a lot of money. So they have these huge code bases, and they don't have necessarily up-to-date or correct documentation for it, and they don't have and trying to port them is a problem. We got one of the big four to have a look at it, and they were just 20 people, 10 years, go for it. And that's a problem. And
I said I apologize on behalf of the Big Four. They are expensive, but someone needs to pay my salary.
Oh, absolutely. No, I've got nothing wrong with that, right? But a lot of our stuff's actually got timelines. Yeah, a lot of our stuff has timelines, which are not 10 years long, and so we've been like painted into this corner that we've got to with like. We've got projects that have been like spec'd as like 20 people for 10 years, and we've got kind of 2 people, or 2 to 5 people, and we need it in 6 months, right? And there's a tension there. Even as a dev who frequently pulls bullshit miracles out of things, that one's pretty special. And so last year I spent a lot of time thinking about like how can we approach this without without a whole bunch of people. We've got AI, we have agents, they were okay at writing code, but what we needed was some kind of provability way of doing it, right? It's not enough to port the software, it is, you have to prove that it was correct and the documentation was right and all of that. And Stats was also going through a stage where they were going through like headcount reduction, like trying to get new people was difficult for them. Trying to start new projects it was very impolitic to start new projects, like new kind of greenfield projects, while firing a bunch of people. That's a big ask, and it doesn't do anything for morale. And so I can understand basically that the project ended up shelved for a while. However, the problems haven't gone away, and when needs must, the devil drives. And so we're back here again porting stuff. But this time, for this talk, we have got the porting engine, or 2 porting engines, one for moving Excel spreadsheets to Python, and I will talk about that like in an automated way. And another one that processes SAS project files. So like not just a SAS file, but like the entire project all at once. And it's a thing. And they work shockingly well. So if last year's one was about provability, this one's actually about context engineering and anti-hallucination, like how to go about doing anti-hallucination stuff. And it's been a big deal at Stats because hallucination bad, provable not hallucination good, especially if you're looking at using them to process, say, surveys and stuff like that. And in fact, one of the surveys recently has been entirely processed using artificial intelligence, which was pretty cool. Hey, we got events. Yeah. So yeah, anti-hallucination frameworks, context engineering, porting software, and I'm going to open source this puppy in the next week, so you will all be able to pick it up and play with it. So if you're one of the big 4 and want to be able to turn around and say, hey, we can port this thing for you, we'll not charge you 25 million, only 20 million, and then like run a piece of software for them, then hey, you know where I am to get me a beer, because I know what the rates are. So let's do this. Actually, I'm gonna start with the SAS one, because weirdly the SAS one is easier to explain than the spreadsheet one. Okay, let's see. Or maybe it isn't. Okay, what have I signed myself up for? Chris, what have I signed myself up for here? And where's my screen sharing done?
I'm sorry. I don't know. Sorry, was there a question?
Yeah. Layer bites off more than you choose, part 1.
Were you looking for the button?
I think I found a button.
You got the button. That's it.
I have.
Just bear in mind that in here you've got a difference between a screen and a window sharing. So just be aware that you've probably done the window share, and that's all good.
Yes, no, the window share is good. I don't need you to see the other kind of shameful things that I have on the window, on the screen. You know, that would be terrible. Like, you know, you don't need to see Stack Overflow open. No one needs to see that. No, I'm kidding. Stack Overflow is dead.
Yeah, no one uses that anymore.
Yep. Okay then. I am going to go get one of our project overview things, and I'm going to hope to God that, I'm going to try this one. I hope to God that this thing is going to let me unpalette, view, open preview, markdown. Hey, beautiful. Okay, so let's talk SAS projects for a moment. I'll blow this up so that people can see it, but we'll talk SAS projects in a minute. So inside SAS projects, there are two walls. No, wait. Inside SAS projects, a SAS project is a zip file. And zip files are going to come up a lot in this conversation. It's a zip file, and inside there's a big old project XML file. And inside that project XML file, there is weirdly fragments of SAS code. Because if they've produced a workflow, inside that workflow, you can write code directly into the workflow screens, and they will end up as SAS that's inside the project file, right? They won't end up like as a separate file, as a separate like SAS file. By SAS, I'm talking a old statistical language package like system. SAS, not software as a service. It is old-ish. It is, and the language itself is still under the control of that company, and like they charge for the engines that run it. They charge a lot for the engines that run it, and so. So for stats, right, having a bunch of stuff in SAS is not just a legacy problem where they don't understand the code and that they don't have coders and that they can't do updates. Yeah. It was big in the 90s. And what it is also expensive for them to run and maintain. So they pay licensing each year. And because, like, typically, one of the SAS people want to. I better check if that's a SAS person at the door. Are they coming here to murder me? Yeah. No. So these SAS people, so for SAS, like, people ported into it, like they wrote an awful lot of software and they can't get off it now. And so SAS can charge what they like, and what they like is a lot. That's, you know, if you have a code base that you can't get off of, and the company can charge whatever they damn well please, that number is going to be big. And for Stats New Zealand, it's very big and it's yearly, and we don't like it. We want off there. So also in these files is a pile of SAS files and there's some other bits and bobs in there, but mostly it's SAS files in this gigantic freaking thing in there. There's like some data sets and stuff. And so what we do is, maybe I do need to go back to code. I'll go back to code for a moment. Or at least I'll show a little bit here. So what we do is, so this project here, because Stats New Zealand doesn't want me to show like actual Stats New Zealand code. I haven't been given approval for like that kind of stuff. So like this has to be on public stuff, and this public stuff is a Netflix data processing system. And so if you look at a bunch of stuff and you're just like, that looks like you're processing Netflix data, why would Stats do that? The answer is that they don't, but the project is roughly the same size and shape as another project that Stats really cares about. And so we can use it as a proxy for that, right? So we can do development outside of Stats on this system as a proxy for running it against a real Stats system, which is kind of cool. Okay. And so we get, and so one of the things that people would be like really keen to try if they were going to port something is basically to like pick up this giant file, this giant monstrosity of a file, you know, this project zip file thing, and just throw it at the LLM and say, look, go port that, have fun. And people try that with spreadsheets as well. It's why you don't see a lot of spreadsheet porting systems. Because if you go drop a spreadsheet into an LLM, which I'm sure plenty of people have done, things go kind of poorly. I mean, it sort of works, but mostly it doesn't. And there's a reason for that. Inside Excel, like XLSX is a zip file, again. Right, and you unpack it, and inside there is this monstrous XML file, because XML files naturally become monstrous over time. If you're a company that just like doesn't give a shit, then it will usually be incredibly verbose and just like this absolute mess. And it's a Microsoft thing where they've basically taken what's the memory that's internal to Excel, and they're just like, yeah, we can wrap X. Like a XLS wrapper around it and just like write that puppy out. And it's much like you think it would be. There is some gold in there though. There's some really cool stuff. So, and we'll get to that. But if you pick up that file and you go drop it into your local LLM and be like, hey, we're going to do some work on this, then that entire Excel, so what'll happen is typically the interfaces for these things will unpack the file and just put the file directly into context. And that context will be big because those files will be big, right? If you've got a 200K XLSX file, then that is 200K of zipped XML with big ass tags that are repeated over and over again. So they zip really well. So they have a super high compression ratio. And so when that puppy is unzipped, it is very large and it is sitting inside context, and your AI system isn't gonna like wear that particularly well. Some of them are a little brighter, some of them are like converted into CSV and just write that in or something like that. But they'll lose like kind of a lot of that information. And so we had to like fix. So anything that we were going to be pushing into the AIs had to be small. If we want them to work properly, right? We can't be sticking these huge things in context and then just saying, "Hey, look, go deal with that." Attention doesn't work that way. Like the whole thing's going to be this. I was going to talk a lot about attention here and like actually how much data from attention ends up in models, but the answer is a lot less than you think, right? So when you actually do something, most of your context just evaporates during as these context heads grab the things that it's meant to do and then shoves them into the layers. And I mean, you can kind of see that, right? You know, if a layer is a certain size and your context is, you know, a million tokens, then how the hell is like you're going to have to lose at least as much to be able to like it needs to be down to the size of your first layout, right? If it's going to be pushed in. And so like a lot of information from context. I'm simplifying it a lot, so don't crucify me on that. I've been building LLMs recently, and I now know more about the topic than I care to know. And I know when I'm overly simplifying stuff, but the bigger your context is, the far less any particular part of it matters, and you are going to need a lot of it to matter for this. And so it's just not going to work very well. Anything where you shove like a big thing in and say, look, I want you to do a big piece of work, it's just going to struggle. And so you need to kind of break these down into ways that it can handle that. And so for our SAS files, right? What I've done here is what the project does is it does this big tracing thing. What it does is it goes into, for the SAS stuff, it goes into the project file and it pulls out the tree. And it can kind of work out from there, like what's calling what, somewhat. What's in the tree has been, like what's in the, the pipeline. A little of what is ordering happens is in there, but not all of it, because bits can call other bits in the code, and that won't necessarily show up in the pipeline. And so what you want to do is you want to be able to turn one big problem into lots and lots and lots of tiny problems, and you need those tiny problems to be reversible, and testable and checkable. And so what we do is we pull out all of the SAS bits in there, and we make a prompt. We get a clean context, and we push it in. And this is literally the prompt that goes in, right? This is the whole thing, and this includes the data. This includes the SAS file that we're pushing in.
All right. Yeah.
Right. So like, there's another one. Here's another SAS bit. And these are like either whole files or fragments, right? SAS is easy to cut up into fragments, so that's what we do. We slice it up into parts. And again, in the talking about my original talk, there was some slides at the end that says, hey, slicing this might actually help. The answer is, yeah, it did. So what we do is we go grab each SAS thing, and we're just like, hey, what the hell does this file do? What calls does it make? What does it include from other things? Because we're going to need to know this. And for each section, and this includes in call macro things. This is sometimes because if it's been included into a pipeline, there is some meta information there, which isn't necessarily in the file directly, and we want to be able to capture that. But there are sections within a SAS program, and so what it does is it looks at each section, and it's just like, okay, like give it a name, give us a start and end line number, tell us what kind of section it is, give us a description of what the section does, tell us what it reads and writes to, what data sets it reads and writes to, and what macros does it define or calls. And this is important because this gives us, this tells us what this thing relies on and what it writes to, and what it defines and what it calls, right? And so you can build a dependency tree from that. And as soon as you've got your dependency tree, you can you can port each individual part by itself and then rewire it back together using the dependency tree. And once you do that, you've ported the software. And so you're basically turning like one horrendously big monstrosity of a port into a whole bunch of tiny little calls out to the LLM. And the reason here that we're actually writing these like the calls that we are making out into a directory here is just simply because the stats, we really want traceability in every stage of like how we came to things. Yo.
So you started off by talking about spreadsheets, and now we're talking about SAS. So sort of this model that you're taking us through for slicing and dicing the SAS code would also apply to the spreadsheet.
We'll go to the spreadsheet one because a lot of what we're doing here applies to the spreadsheet, but applies in a slightly different way. And so we will get there. But the main thing I'm trying to show here is, like, if your calls to the system is like 100 lines for your entire prompt, you know, and that is it. Like, that's the whole thing. Like, empty context, here it is, 100 lines. You know, that's the whole deal from beginning to end. Then almost certainly what you push in works. What comes out is correct, because because almost everything, like attention, picks up everything right at that stage, and so you're not getting like these bits that are like you're not muddling things up. You're giving it a nice, easy task that's very straightforward and a very straightforward data set that is very, very small. And LLMs do incredibly well under those circumstances, and so we go get some stuff out from there. And then we don't trust it within an inch of its life, right? So we will get out, that's extracted code, that's the thing. Right, so we get out our analysis of one of the files. And so it, you know, for each section, we'll pick a section that's interesting. Here's one. Drop temporary sorted view. Which line does it start? Which line does it end? Etc. 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 Oh, I'll have to switch back and show you something that's interesting. So I'll go back to one of the prompts here. Inside this prompt, you will see that I stuck line numbers at the start of things. And that is because if you ask an LLM how many lines, you know, which line number does this section start, it cannot tell you. They are terrible at counting. They're awful at it. You've got to give them like literally, you basically got to draw a little mark around everything. Go like this right here. This is the piece of information that you need. And you can't rely on it to work it out itself, because most of the time it can't. It would never be able to work out like which line number most of these things is, unless you literally told it in there. And you know, and so we do, and that'll become important in a few moments. So up here we get our fragments, and it tells us what it does. It actually it tells us the starting and end line numbers. And what we do at that stage is the code goes out there and it grabs the code fragment that's actually in those lines. So this is like when it says these are the header comments, these are the header comments that are there. And we know that they're right because, or at least we know that they are these line numbers between these two. We don't know if those two numbers are correct, but we do know that it thinks that this is the starting and ending line. And because we've put the starting and ending line numbers there, it's probably right. And we've got a description about what this thing is, like which each of these sections do. And then what we do is the next step is we go and pull the code fragment out, and then we say, hey, we've got some code fragment, and we've got a description of, we've got this description, and it's in SAS, and we would really like to write some code that does this. Is this reasonable? So if it's got the line numbers wrong, or it's done a bad read on the code fragment, or the description is wrong, then that stage is going to fail, right? It is because we've taken like the question in one direction and then reframed it and asked it backwards. It is very unlikely, and it's even a simpler call, right? Because we're just saying, hey, you know, we're trying to do this. Is this good code for it? then and does it read this, right? And so it's if any part of our original one direction went wrong, then the reverse call is going to turn around and say, well, no, this doesn't make any sense. And so for a hallucination to go through, now you've got two very simple calls that you have to make that fail. As it happens, our original call that we do over and the call that we do back, that is run on two different models as well. We port it twice. We analyze it twice and we reverse it twice. And so like 4 calls are made, 2 models, 2 forward, 2 in reverse. And so it's very hard for it to hallucinate its way through there. We've basically like kind of trapped it. In that if any one of these fail, well, then we throw it out. And we go through processing and we log that we had thrown it out so we can have a look and see what our hallucination rate is. And so we end up with extremely high quality stuff that is very much proved. And then we do some extra tests on top of that, because the reading and writing data set stuff that we're doing the extra processing on, well, that ends up in this big call tree, and that call tree has to like make sense. And we get something that looks over that and goes, well, does this make sense? Does this thing hang together as a whole? So if there's anything hanky that happens at the start, even if it gets through that, then it'll get, it gets caught up there. And then later, we then port using all this information. And that port, we've got our original data sets. And so we run it through the original data sets, checking the input and output. And if that's wrong, then it gets picked up. And so we've really boxed in the LLM. We make sure that it is very hard for it to get anything wrong. Yo.
Better.
Yeah, on this boxing in, so you already had this SAS processing stuff, or did you write it specifically to pull out the data you needed?
Okay, so our initial thing here is that we do a big we have a deterministic thing that goes through and pulls out all of the SAS code in the project, and does and the stuff that's in the what's it called, in the project XML. And so there's a lot of deterministic steps that happen before we hit the LLM stage, and then this LLM stage, like where this call is done on 2 different LLMs to make sure that, and we expect that that the results that come out, apart from the description, should be identical. Like the name and the description, like they don't have to be identical, but everything else should be, right? There's nothing in there that should be not the same, right? And so we compare those, and we're just like, look, if there's anything in this that's not the same, we throw it out. And if it gets through that stage, well, then we've got these descriptions and we've got this piece of code and we know that the piece of code is like from the line numbers it said it is, because we don't use the LLM. We're not asking the LLM for like what was the code there. We just pull those pieces of line numbers in the original file. And then you
probably had good reasons to choose this approach, right? But there are more people who have to deal with really large data sets. Databases are a typical example. So I could imagine, why not put the data in the database so the LLMs are good in generating SQL, or second approach, why not use MCP and sort of query this? So for you, I suppose this must have worked better than the approaches we more normally see. It's very complicated. You generate SAS, you run it, you check it. It's something else.
Well, it's an orchestration layer, right? It isn't actually complicated. It isn't actually that complicated. Right? We're not doing that many steps here. But we are writing a piece of code. So the porting engine is basically a big block of orchestration code that uses LLMs. Like, it'll call out to them and do some work with them. But most of it is deterministic. We're using the LLMs like to the minimum required, and where we are using the LLMs, we are we're basically treating them as undeterministic, probabilistic systems that you then have to do probabilistic stuff around. And you need to try and like make sure that the results come out right. And then we do a bunch of deterministic stuff afterwards for the testing, right? The tests have to be deterministic, and we don't let the LLM write the tests, but like, it's a well-staged problem. Like, we can automatically create those tests, so we automatically create those tests. So basically, we're turning what is a really nasty problem for an LLM to a whole bunch of incredibly simple ones, and then testing the Jesus out of them to make sure that none of those fail.
So like this, you kind of skipped the part where you've actually created these prompts. So those prompts, for example, you've got presumably just the standard.
Oh, okay. Yeah. So if you'll notice here, if I go through these prompts, they all look very similar.
Yeah.
Right. And it's just adding the code on the end. So there's a piece of code that's producing this, right? So we drop so how it works is we drop the project in one side. It unpacks it in memory. It processes the XML within an inch of its life to pull out the information, grabs all of the SAS code, writes it out to a set of directories, produces a bunch of prompts from those, and then runs the thing against a set of things against those prompts. And then we reassemble everything afterwards. And
so you're executing each prompt essentially in Bash, I presume, to just sort of run it through as a cycle.
Yeah. And they can be run in parallel. That's the other thing, right? So this has completely changed how Stacks looks at porting software, right? And in fact, it looks at processes and AI in a big way. Which I was going to get into later. And the reason it changed it was economics, right? If a porting project from beginning to end, right, costs you, 10 minutes and $2 in tokens, then rather than years of work, then if you want to change any way about how you went about it, then you tweak the code. You treat it like a compile stage, right? So you tweak your approach to it, and then you rerun the entire porting process from beginning to end. So we, you are refining the process that you're using for porting, and you're treating like the software like it's a bunch of prep stages for a coding team, and then you're handing the coding tasks off. Anyway, so in the end of it, you end up with. So I'll try and get this into a much more viewable state.
Sure.
Yes.
Just a very short question here. Which part of this process is, you mentioned deterministic, which one is non-deterministic?
So
at what point what you showed us becomes deterministic? I'm just saying becomes your porting project, you rely on it, you build on it, you can run it anytime.
Yes. So the deterministic parts are the things that parse the XML, the things that pull out the all of the SAS fragments, the stuff that does the first pass analysis on everything, because it's looking at stuff from inside the XML. The non-deterministic stuff is we've got prompts, and then it does prompt generation, and then the non-deterministic stuff is running those prompts through the system, but we're trying to turn that into as much of a deterministic process as possible by running it through on more than one engine, more than once and comparing the results and then running them backwards so that we're taking the description and saying, hey, you know, given this description, does this code make any sense? So we've got a lot of stuff in there so that we're boxing it in so we can't mess that up. And then as soon as all that's done, we're back into non-deterministic land, right? We're
reassembling things. Yeah.
Right, we're reassembling it, right? And so what happens is that each of those things that we were seeing, you know, because we've now got a big stack of outputs that are less like this is what this relies on, this is the stuff that it produces, right? We can produce a giant dependency graph. We get 2 giant dependency graphs. As it is, there's basically 2 programs within the SAS thing, and here they are. One is for dealing with ratings and streaming, and the other one is for like looking at the stuff individually.
Yeah, right. And our Netflix example,
yeah, on our Netflix example. And so these are what all the nodes are, what they do, and again, what they do is pull them out. And then on the per file details, when we pulled out the the line numbers, you know, we've got a thing in here saying show me the code.
Yeah.
And then I fucked up the color scheme for it on this because I was doing it on a white monitor initially. And
so what we're looking at here is sort of like an overview of the entire thing. Once it's
right.
Yeah.
And so this file contains everything that you would need to do to recreate the project, right? It is a large scale analysis. It is like a little bit of fragments for each part. It is how they fit together. It is what data sets that they are, what tables they're reading from, what tables they're writing to, what files it's pulling off the file system, like freaking everything. Along with, you know, descriptions and stuff like that. And so what we can do now is we can go through that same kind of process where we take these fragments, like the SAS fragments, because we know about the SAS fragments, and we can deterministically sandwich some code around them that says, hey, we know that this thing is reading this you know, this file or these variables or whatever. Please output those at the state before this thing runs, and we know it's writing out these things, and we know that it's like producing variables that other things consume, right? Can you take these variables and write those out, right? And so now you've got all the things that it's pulling in, all the things that it's pulling out. You can rerun that system on production, and now you've got all of these, each fragment inside your program has now got, so all of the test data that comes in, all of the test data that comes out, you know, everything that has ever been run through it in production, if you run it through for the last, you know, 20 odd years. And then, and it's in an automated way, it's fast.
Yeah.
Right, and then you can literally, when you go tell it to turn it into Python, you can then push that data through and see whether the data that comes out is the same. If it doesn't, then it was a bad build, and you can just do it fragment by fragment until you get a good build. And then
you can take fragments,
you reassemble it,
more fragments together, and do bigger chains, and just get kind of bigger and bigger. Yeah.
Right, and so the reassembling stage, right? That's deterministic, right? I mean, as soon as you've tested all the fragments, you push it back together again. You do a final testing run from beginning to end because you've got that data from production, from the old system, and then you can call it a day because you've got a system that is identical. Like you've managed to do a porting effort in a way that works, right? You have gotten them off SAS, which is proprietary, you know, expensive, and, you know, obviously going to be a long-term problem for stats. And you've got them onto Databricks, which is proprietary, expensive, and obviously going to be a long-term problem for stats. And so,
that's the problem for the next 25 years, for the next generation, right?
But you've also, as a side effect, now actually got documentation that's correct. which is a neat trick, right? And in fact, what you've got is a system where you can change a little bit of thing to saying this is what your target is, and then you can run rebuild. And so now you've got something that is like actually independent of languages and platforms and stuff. Like a few lines have changed, you hit the go button, and now you've got something written in R, you've now got something written in Julia, you've now got something written in like local Python, you've got something written written for Salesforce if you really wanted to cause yourself problems in the future.
Sorry again. I have two questions. One maybe kind of going deeper, but another one maybe another higher abstract layer. So what you're showing us here is a result of the how would I express this, of the code analyzer, and actually analyze you and builds you the analyzer says code and explains to builds you exactly how it's built. That's why it's relatively straightforward to put it in, I don't know, Python, to look at it, how it's structured, produce the same output, you test it, and so on.
Yes.
And that is actually how you came to this point, as complicated as that might look. Actually is a recipe. It's a repeatable recipe, because nothing stops you now with it's some kind of a very close to automation. You can put another piece of SS code and it should produce something similar to this, except it accounts the new elements that you're going to analyze and add to your knowledge base and so on. So let's say this, for argument's sake, that maybe with 25% investment on different, let's say, kinds of SAS code, you reach the point that you can analyze maybe 80, 90% of your overall SAS code.
Well, what's happened in this instance is that we haven't run into any SAS code it doesn't just process and work on. So, which is pretty cool. Now that might be that we haven't tried it on some of the more pathological cases, but like when we do, what's going to happen is that we're going to update our process, right? So we'll update the orchestration layer, which means that we've updated our process, which means that every thing that we do from here on will include those extra steps. Right?
So that's my next question. Sorry, Chris. Just one next question comes here. This is still at a level of, let's say, a single, let's call it a program. If program is something, 100, 150 lines of code in SAS, kind of a file, right? But in good old times, total is a good, 4 screens, not more than that. And then you analyze lots of them, but you're still finishing with the analyzing the inputs or outputs of one particular routine or procedure, let's call it. I'm looking this here, and this kind of way, you have many of these, especially with inputs and outputs, who calls whom and all the stuff. That I'm trying to imagine myself the graphical representation of that, like this kind of old good old functional diagrams in the past. So have you built something like that, or have you probably reached the same conclusion yourself?
This is producing work ratings, which is going into a ratings format system, which is making a macro call to calc data and ratings. And in fact, if you look inside the Mermaid stuff, we've actually got Mermaid code. This is a Mermaid chart, right? And so inside the Mermaid code, it's actually got descriptions about what's in here as well, like inside that block. And this is something I'm going to talk about when we get to the spreadsheets, because this is exactly what we did inside the spreadsheet stuff. We take our spreadsheet stuff, we put it through, we know that there are blocks within our spreadsheet of like, hey, this whole row column gets multiplied by this column and subtracted by this column and then divided by this column, right? We've got a formula over here. So that formula is referring back to these things. So there's a dependency set there, and you can produce a dependency graph. And so we produce a dependency graph, right? So instead of this eye-wateringly large Excel SX file that we're going to try and push in there, what we've now got is this tiny little dependency graph chart, like written in a charting language, so you can like just display it on the screen. But the LLMs are like more than happy to read that, and so you just push that in and say, hey, make me a Python representation of that, and it's just like, yes, boss.
This is super useful for my problem. Thank you so much for this.
Yep. And then, right, because you've got the spreadsheet, right, when you do that analysis stage on the spreadsheet, you also pull out what the values were in the cells. And if you've got like lots of spreadsheets in a directory, because the spreadsheet, the dependency tree that the spreadsheet produces, along with what operations it does, if more than one of those spreadsheets have the same dependency tree, then it's the same spreadsheet, probably with just different data. And this happens a lot inside stats, right? Because it'll be like January, February, March, April, May, June, July, right? And so you'll just have these directories of like massive amounts of spreadsheets that are all very similar. And structurally similar, and you can hash your dependency tree, and know if these things are in fact the same structured spreadsheet, which is cool, right? Because you also have got because you've made a dependency graph, you now know what values have gone into the spreadsheet, and you know what values the spreadsheet have processed into. And you know what the values that the actual spreadsheets did process to. And so now you've got a pile of inputs, you've got a pile of outputs again, and in fact, even like multiple sets, if there's been more than one spreadsheet that's using the same structure, then now you've got tests, right? You've got all the data you need for the system to be able to produce an automated test. So deterministically, you produce your tests, and then when you hand over like this small diagram over to your like agentic coding engine and say, turn that into Python or whatever language it is that's flavor of the week, then it ports it, it runs the tests. If the tests pass, you, my friend, have ported a spreadsheet to that language, and it's fast. Right, it's crazy fast, and it is in fact so fast that I wanted to know what the hallucination rate was, what the failure rate was on all the tests, right? And the failure rate was like lower than 1%, and even then it was the system timing out rather than it not actually making the port. And how I know that is that I just was like, fine, port it 200 times. Yeah, do it, right? And 10 minutes later, it's done 200 ports, right? It's like, because the task is trivial, you can do that. You can get away with that. There's nothing stopping you, right? And then pull actually real stats out, which is what we did for the porting engine. So in this case, this is SAS. This is like everything from beginning to end that you may want to know about like the SAS thing. And I'll move over back to our porting thing. And hey, we've got ourselves a is this the right one? Oh, no, not the Mermaid plugin. Please, no. Don't do this to me. Okay. So, and so what we do when we're doing a run, so I'll pull one of these runs out. Oh, it's an interesting one. Here we go. Okay, so we get this is the entire code for doing the port, right? There is nothing difficult in this, right? The entire port thing for porting a spreadsheet from beginning to end is just tiny. Sorry, this is the code from a port. So this is the spreadsheet recreated in Python using things. But the code for actually doing the port is really small as well. This is our verifier, and the verifier, that is our testing framework. It is, the verifier is the same each time we do it. And we've got 3 directories. We have our inputs. So these are the different things that are pulled out of the spreadsheet that's useful. The expected values, which is what they pulled out. Oh, sorry. These are inputs from our test. This is what's expected. So this is what came out of the spreadsheet in the end, right? So our phase summary, you will see that the phase summary is basically empty. Here, it expects it to be full of data, right? When those inputs are run through that model, it produces this directory of outputs, and we compare the inputs and outputs. And if they are the same, we have done a successful port because we've done a test, right? We've finished our testing process, and that's it. Like that. That's the whole thing. The biggest thing that I can get, that I'm going to try to get to you though, all is our prompts that we push in here. So for that port, the prompt here is, you are an autonomous data engineer. Your task is to write a Python script that reads these CSVs and outputs these others. Let's see if I can get the whole thing. Strictly matching clean CSV schemas into the actual directory. This is the logic you must follow. And this is a diagram of this is a diagram of of the dependency thing. This is literally our Mermaid chart. And if I change this, if I rename this to prompt markdown, hopefully, and I go to command palette and go and preview this puppy. Ta-da! We've got like our prompt is literally a chart that you can look at, which is kind of neat. Well, it would be a chart that you can look at if like the screen was higher, was better, and I could zoom in, which I cannot. But it's got bits in there, like it tells it like what the rows are doing and all that sort of stuff. And
so sorry, how did we get to this chart?
So this chart here is the prompt, which is wild.
Yeah,
right?
That's the prompt.
I'm listening here. They're all pretending they know this, right? And I'm just thinking, who's clueless as I am? Who's going to ask how this magic happened?
Yeah,
okay.
I know, Nisha. I'm just asking for you.
Of course.
Okay.
I'm not.
So inside our prompt, right? We're telling it that it's like Python, and Mermaid's an actual like data format, and so this here is the actual data visualization like written there. It's like a doc file if you've ever used Graphviz.
I get what Mermaid is, but how did we generate the Mermaid? Was that a deterministic process that we pulled out? Right.
Yes, that's a deterministic process. We have literally pulled out. We have something goes through the XLSX like big XML thing, and pulls out the parts that are are telling like this block is reading from this is doing all this stuff here, because Microsoft actually has the the call chain in there, because they want to know if you're changing this part of the spreadsheet, like what other cells do we want to update.
So you're
alluding
to the secret source, like there's all this stuff, but that's the bit you were trying to get to. That was the nugget in there.
Yeah. So this is the nugget that we actually care about. And so we produce this this chart, and then we're like, hey, these are the files that we need you to read, and we want you to produce this, and there is some a boilerplate thing in there. With the reason that we had the boilerplate, and this boilerplate is generated like knowing a bunch of the stuff that came out of the dependency diagram. And the reason that the boilerplate's there is because if it produces it the same way, that means that we already know what it looks like. We know what the calls look like. We can automatically test it, right? And then in here, we're telling the agentic engine, by the way, you can test this while you're doing your coding. Like, so we literally grab a Gemini prompt, command line, and we pass this file in to it as this is your prompt, and then we just let it go, and it does the rest. It produces us our code.
So just to take a step back again, so the graph, that part,
yep,
the Mermaid, what format was that in the Excel zip file?
It's in this giant fucking XML file in there.
Oh, okay. Yeah. How did you convert it to Mermaid? Did you have to run that through an AI to convert it to Mermaid?
No. We do not need to do that. That is the that's R1C1 run markdowns. We used to have a really good, these are the actual spreadsheets here that's doing the processing. So our test spreadsheets. There's, right. Okay, here we go. This is the secret sauce here. So we go pull our pull the file out, and then we call dump sheet to markdown. Oh no, that's if we're doing the markdown stuff. Let's have a look, see. Yep, there we go. Password. There we go. So this here is cell nodes, pass worksheet, all that sort of stuff. So this is pulling out the cells. Like there's a program, a library inside Python that allows you to like look through spreadsheets. And so so we read the spreadsheet, and we pull out the formulas and stuff, and then we walk through that list, generating, finding the dependencies, creating a cell node, and stuff. And this nodes thing here, this is a Mermaid node. So spreadsheet in, Mermaid nodes out.
Oh, okay. Nice. As easy as that.
So yeah, there's not a lot to it.
Like Chris said, you might not have picked that up in the chat, but something like that, you could easily turn into a skill. So I mean, that would even just be useful to be able to see the logic in a freaking spreadsheet presented as a Mermaid chart.
Yep.
That'd be really useful.
Very, very useful.
Yep. And there's some stuff in there for actually like producing the diet, working out the dependencies, right? So
Are you gonna be
then take our
open
nodes.
this?
We then take our nodes and we actually do some processing to turn it into like a directed diagram, and we do some checks and stuff around them, and then literally we start our Mermaid diagram. We're just like, hey, this is our writing out. Here's the beginning things. We want to have some colors for one of our things here. We want to add some nodes, and then and we produce some JSON in here. And this is interesting. I will get to this. So one of the secret sources that we've got on this is when we produce our Mermaid diagram. Where's our Mermaid diagram? We produce two of them. Well, actually, we produce more than two, but the ones that we're interested in here is unannotated, which is it's it's a Mermaid thing, but we've also got commentary in there, and the commentary is actually like, look, these are the formulas here. This is the formula in R1C1. R1C1 is like a universal thing inside Excel spreadsheets. So when you write a formula and then you grab a thing and you drag it down and it's done a whole bunch of stuff there, then what it's done is they all have the same formula in them. Not they have a formula that is offset, like when you see it say +1, +3, +5, whatever. They actually have the same formula in there, and that formula has got stuff in there where it refers to the rows and columns. So there's like a formula in this meta formula for like describing how to do that. We're using that meta formula in a big way, and this is what this thing is, what R1C1 form is, and most people don't know it exists. And so this is entirely deterministic, and we will get on to because there's two non-deterministic sections. And the deterministic bit goes through and writes all this stuff out. It tells us the formats. It writes, what type of cell it was. Tells us what data was in the cells, which is useful because we turn this into our tests and the like. And then we, go through that. And then we pick this file up and we go shove it back in again, back into the LLM with a small comment on there saying, hey, look, here's this file. Can you tell us what all these bits do? And so inside the annotated one, I'll bring up the annotated version. I'm gonna have a pen in the ass. Okay, in the annotated one, there is like, hey, this is doing variance calculation. So it's the LLM like turning around and going, see what this block is? This block is variance calculation. This is kind of what this does. And it does that just by like reading through the file and going, yeah, okay, I get it. I see what you're doing here. Like going through this. And it's just annotating it a bit so that it makes it like, what does it do? Why does it do it? And we don't know if this is correct, but we do the backwards pass where we grab each section and we say, hey, look, here's the formula that it's doing. We think it's calculating total variance. Is that right? And if that passes, then we're just like, yeah, okay, fine. Like it's done a force pass, it's done a backwards pass. We could run it through multiple LLMs if we cared about, like exactly the same trick that we do with the SAS code, but we can apply it here. But we're only doing this for documentation, and then otherwise we literally produce this prompt file. So like everything up to the stage here, this prompt file is deterministic, and this prompt file is the thing that's handed down to the LLM, and we've already got tests in place to know if it works or not. Handing those tests down to not going to say LLM, the agentic engine. And the reason that that's interesting is because if you just hand it to the LLM, it'll just try and do a first pass of the code, and it'll probably be garbage, and you'll probably have a high failure rate. So we go past it to like the Gemini agentic coder or the Claude agentic coder or whatever one is flavor of the week right now, and we get it to do the dirty work. But we tell it how to test stuff, and so that before it even gets back to us with like, "Hey, I'm done," it's already run the tests a bunch of times and like done its set of debugging and stuff like that, so we don't have to. But we don't let it mess with the tests. We don't, right? We regenerate the tests afterwards, and then we run against that because we're not. We don't trust the LLM not to edit the tests to pass, because it will. You just watch it; it absolutely will. And so you've got what's it called? You got to sandbox that puppy. You got to sandbox it, but good. Make sure it's not allowed to read anywhere, write to anywhere it's not allowed to write. But outside that, it goes. Oh, and then there's a final pass where we pass it to the LLM. We say, "Here's the code. This is the test. Is this cheating?" And one of our runs, it was just like, "Yep." I was having a look at it, and it was like, "Yeah." It had found the outputs and it like hard coded some of them in, which was a bit grim. But there we go. That's our talk.
That's pretty impressive, dude. It's pretty impressive.
Oh, so let's talk timelines, because this was actually really cool. I'm not going to explain all the bits that led up to this, because
for reasons.
I might have been spiked coding when I write this. Have any of you ever done that, where you just sat down and you're like so offended about how someone's actually approaching someone that you sit down and you just like absolutely bang out some of the best code of your life, and it's just a pure spite to like go, as a like, go fuck yourself. Great, this is being recorded. Excellent. Okay. So absolutely 100% spike code. This whole programming thing, because I was using, obviously I was being a scrub and vibe coded this as a thing. This took 4 hours. This whole thing, 4 hours end to end. I sat down and built the entire.
Don't tell that to anybody.
This was 4 hours, and the SAS port. This was overnight. This was an overnight run.
Hey Blair, just to interrupt, although you said it took 4 hours to vibe code it, the domain knowledge around it to actually be able to do that and build
35 years.
Yeah, exactly. So like
oh yeah.
Don't discount yourself. Like vibe coding isn't bad if you've got the domain knowledge to back it up.
As long as you don't tell it to senior manager or politician.
Yeah. Well, no. So I absolutely did this as like spike-driven development. I'm totally making that as a thing, So it's so these kind of engines, where if you like the anti-hallucination stuff, if you know how they work, and you've got like a very clear idea about how you want to get, about how this multi-force passing forward pass and compare, and the forward pass and back pass and like do checks, and the final stage testing and stuff like that. I mean, this was built almost entirely off the patterns that I did with the first talk that I gave, the egg talk, like unscrambling the egg. So this was kind of 8 hours of spike coding after thinking about the problem for a year.
Yeah, that's right.
So that puts it in perspective a
It
little.
all came together.
Like, I didn't sit down here from cold, right? I had a very clear plan about like how this thing was going to work. But the first time that it actually just spat out wicked code, like, because it did that real quickly in the piece. And I spent more time on this bit here, showing stuff than I did here. And in fact, here we've got all these ticks, right? And these ticks are like, yes, we've checked the lineage. That it's done the force pass, that it did the back pass, that there was no failures when it tried to do that. Like, this is here. Correctly identifies macro call used the table setup. We know that that's correct because it's done that back pass, right? It's gone through the anti-hallucination stuff. And I have some symbols in here for if it messed it up, like at all during any of the times, then it switches it from a tick to being like, well, might be a bit difficult. But as you can see here, like none of those have shown up. And on like 90-something% of the runs, they don't. It just works. And I don't mean, in the usual software sense of it just works, it just works. No, I mean, it actually works. So that's kind of cool.